Hey, this is Jason again, and we're back with the next in our series on rotating reference frames and how we can actually relate that to the rotation of the Earth and show that the Earth is actually a sphere and is rotating and what we mean by all that. We're also going to continue developing the idea of the Foucault pendulum and get close to the three-body problem and Lagrange points at some point. So this is the second in the series. So let's continue on. First thing is that we're looking at is last time in the first video we derived this equation which shows the effective force on the left hand side of the equation due to the rotation of the reference frame around some sort of rotation axis. The capital F vector that we see there is the only true force in the system, whatever it is. It can be a series of forces, it can be just one, but that's the only true force, meaning it's the only Newtonian force that has an equal and opposite reaction. The other two terms are actually cause accelerations and cause forces, but they're only the result of the rotating reference frame, and so do not have an equal and opposite reaction inside of them. So that's interesting, and that's why they're called fictitious forces or pseudo forces, because they do act in reality. It's just they do not have an equal and opposite reaction. So on the left-hand side, that's why we denote the mass times the acceleration with a little tick mark there that shows that the tick mark is the things that are measured in the rotating reference frame. So we're now going to look at the effect on things on the surface of the Earth due to its rotation. So the first thing we're going to look at is centrifugal acceleration. In fact, the second term on the first term on the left-hand side of that equation that we looked at before, that is actually the centrifugal acceleration. That's what we're going to analyze. So let's go back and we're going to reframe this thing from what we saw in the previous video. We're going to define our non-rotating inertial reference frame to be the center of the Earth. And that allows us to say, okay, up or the z-axis goes towards the North Pole from the center of the Earth, and say the x-axis goes out to some point on the equator, and the y-axis would go 90 degrees from that also along the equator. We could define that wherever we want. Maybe its surface is at 0 degrees latitude and 0 degrees longitude, whatever you want. But that's the inertial reference frame. Now the Earth rotates around that inertial reference frame, and so at the surface of the Earth, or some distance from the center of the Earth in that inertial reference frame that's rotating around, we have that R, that little green R vector. Now we're using the surface of the Earth, but we could just assume that there's some goo or layer, but we're just positing that we're looking at the surface of Earth. And so R can be like below ground or above ground or in the air or what have you. But the radius of the Earth is a different thing. Now, how fast is this rotation? Well, omega vector, which is what the arrow means, shows the direction and magnitude of the rotation axis. And the rotation axis is through the North Pole, and we consider it up to be the North Pole, and it goes through 2 pi radians in 24 hours, so that is 7.27 times 10 to the minus 5 radians per second, and that is the angular speed with which the Earth is rotating. And if we then say that we're going to have our now rotating reference frame, so someplace on the surface of Earth will be our rotating reference frame, and it'll be situated at some latitude lambda above the equator. And once we get to that rotating reference frame, we now then say, oh, look, there's our x's and y's and z's, and that's our frame that we're going to be looking at that is rotating around the inertial reference frame. So the rotating reference frame is a non-inertial reference frame, which is important to remember. All right, so we want to have something that is sitting on our inertial reference frame, an object stationary on the Earth's surface, so probably like a tree or somebody falling asleep or what have you. And the object's apparent equation of motion, which we can derive from above, is now the mass of the object times its acceleration tick inside of the rotating reference frame is equal to some force, and I use the lowercase f because whatever that is, we don't know yet. And that'll be, we'll take away, now we're looking at only the centrifugal aspect. So it's stationary. Remember the previous equation had two parts, one for the location and one for it if it was actually moving inside that reference frame. And we're saying it's not moving inside that reference frame. And the lowercase r here is a vector from the inertial reference frame to its position, wherever that thing is in the rotating reference frame. So that lowercase r is the vector in the inertial reference frame, and we've got to transfer that to the non-inertial reference frame shortly. Okay, so let's make a lot of simplifying assumptions. First, we're going to have only one force, one true force, the force of gravity, so we can replace F arrow with mass times the gravitational acceleration. And the gravitational acceleration will always point towards the center of the Earth. And we're going to also assume, just to help make things better, that the Earth is a perfectly flat sphere. You know, why not? It's not a bad assumption, but you know, it's good to tell you what we're doing here. And further, we're going to assume that the object is on the surface of the Earth. It's not jumping up or down. It's not like 10 feet up or 10 feet below or 100 miles up, what have you. And so the displacement vector from the inertial reference frame, which is at the center of the Earth, to the rotating reference frame shall be the Earth's radius vector. That actually makes things a little easier. Also gives us a number to work with. The acceleration on the Earth's the object is then the acceleration measured in the rotating reference frame at the Earth's surface, which is really what we're going for. And now that equation simplifies to the above. So G here is the G tick is the effective acceleration at a point on the Earth's surface due to equals the actual true force of gravity, which is G without a tick arrow, subtracting, you take away this centrifugal parameter. The G always has a magnitude of 9.8 meters per second squared, pointing downward, which in this reference, which in the inertia, in the rotating reference frame is always negative z. But the centrifugal acceleration is normal or perpendicular to the Earth's axis of rotation. And it always points away from that axis, always does. Centrifugal acceleration always points away from the axis of rotation, so it makes it a little complicated on the surface of a sphere because you have there's where our latitude thing comes in. So the magnitude of the centrifugal acceleration is omega squared. See, there's two omegas in that cross product times the r. But r is the radius vector from the center of the Earth, but we want it from the center of the rotation axis, not from the center of the Earth, and so that's where that rho comes in. That's not a p, that is a Greek letter rho, and that can be represented by the radius of the Earth times the cosine of the latitude, and that gives us the distance from the rotation axis at that latitude. So the radius of the Earth is approximately 6.37 times 10 to the 6th meters, which is a long way. And that means that rho squared r has a value of 0.0337 meters per second squared, which is a lot smaller than 9.8 meters per second squared. It's important to note that this is hundreds of times smaller than the gravitational force. And therefore, the cosine of the latitude means that at the maximum, it is maximum at the equator and quickly drops to 0 as you get closer and closer to the poles. Let's just remember this number and continue our quest. So our setup so far, we're going to make choose the Cartesian axis, the XYZ axes, on the rotating reference frame such that the Z tick, and this is always the tick marks, always represent the things in the rotating reference frame. Z tick axis points directly up, so wherever you are on the surface of the Earth, look straight up, that's Z. X tick is going to point directly at the north rotation axis pole, not the north magnetic pole, and y-axis is going to point directly to the west. So here, that's out of the picture, directly straight towards you out of the video. There's our rho in the orange, which is the value of the cosine of the radius of the Earth times the cosine of the lambda, which is the latitude. And so I actually wrote that in there to show where we have two actual accelerations. The yellow arrows are the true accelerations or two accelerations that we're going to be looking at. Downward is towards the center of the Earth is the gravitational acceleration. That is a true force due to something. And the which means that there's an equal and opposite reaction to that force. The centrifugal acceleration has no equal and opposite thing associated with it, so it's a pseudo-force. But it still does things, even though it's called a pseudo-force, but it's a force that exists simply because of the rotation of the reference frame. I'm going to keep saying this because it's really important to note that people always hear that pseudo-force, fictitious force. No, these things are real, but they do not behave in the Newtonian style. I mean, they don't behave in the third law. Okay, so we have two forces we're working with, two accelerations we're working with. And there's our Cartesian reference frame. So let's kind of rearrange things just a bit. Let's extract out the parts and rearrange it so it's kind of like at the surface of the Earth. So x tick points due north, z tick points upwards. There's our little lambda, which shows the latitudes, deviation, how the centrifugal acceleration is deviating as a function of latitude. And the true gravitational acceleration, as we expect, is down, or into the surface of the Earth, straight down. Now, we can decompose the centrifugal acceleration into two components, which are shown in the blue arrows, one going up and one going to the south, if we're in the northern hemisphere. So we now have the omega can be looked at as the rotation of, we're going to need that really quick, right? Because the rotation axis, the rotation vector, has two components. One that is a z component, which is omega sine theta, or lambda, which is the latitude, and one that is omega cosine of lambda, which is for the north-south direction. Now the r is pointed downwards and the g is pointed downwards, and they are vectors too. So these are our three vectors that we're going to really be working with. And that's what we saw before, so we actually had to define them in this parentheses notation, where the x is the first entry. So x tick is omega cosine lambda. Y tick, which is out of the frame. None of these things go out of the frame. The radius of the Earth is not up and out, nor is g, and neither is the centrifugal force. The centrifugal force acceleration is vertical or northward. It has nothing to do with the left, right, west, or east direction. So that's why we see a 0 in the second tick for it. And the centrifugal acceleration does have a z component, meaning up and down, because we're always going away from the rotation axis. So there will be some portion of that. And r always points towards the center of the Earth, as well as g. So now we've got all our stuff defined. We now need to do the vector cross product below. And vector cross product, those are just times. That's a very special thing called a cross product. So we need to review what we mean by a cross product, because we're going to take the cross product of a cross product, which is can be kind of crazy. So we got three vectors. We're taking a cross product of omega cross r and then omega cross r. So let's look at that stuff, because you probably are rusty. Who goes and looks at this stuff on a daily basis? Probably not you, and I'm going to assume you're not. So here we go. Vector cross product is defined as follows. We call it the curl because it's used to define flows around points. That's a good way of thinking about it. But we always have two vectors. we're going to define it using the letters A and B. So we have vector A and vector B, and they can be decomposed into their x, y, z components. And there's a little there's a part that's going in the x component for each of them. And that's what the A sub x, A sub y, A sub z, and B sub x, y, z all indicate. So these vectors can be decomposed, just like I decomposed the centrifugal acceleration into an up and down, down, left, right, and backwards and forwards. Any vector can be decomposed into its constituent parts that when added together r the vector. So the definition of the curl, or cross product of two vectors, is that crazy looking formula below. And so you can see that for each of the directions x, y, and z, or z if you're over in London, the x, y, z components, none of them contain the components of the vector x. Like say, notice the first component in x does not contain a component of x, meaning you only have the components of y, z, meaning something that's perpendicular to that axis. So we're always looking at a rotation around that particular axis for that. So these are all frame rotations or rotations. So if there is no z component, or if there's no y component, let's say there's no z or y component, then you only have an x component. That means you're rotating around the x-axis. If there's no y or z component, you're only rotating around the y-axis, right? So it's pretty interesting in that regard. But this is the definition of the curl and cross product. So what we'll do is we're going to now take the values of those vectors that we have and plug it into this very nasty equation, knowing that, remember, the y components are all zeros, so that'll come up, and many of the components are zero. So let's go take a look at what that means. So let's first, this is a crazy looking thing, and here we go, here's equations. But first we're going to look at omega cross r, and I've kept the definitions a little side off there, and I'm just plugged in for each of the a sub x, a sub y's, and b sub x, b sub y's, their appropriate values for omega and r. And I put the dots in there as a way of showing multiplication. And I've taken the x, y, and z values from the parentheses definitions to the left in that little subpart over there. And we see that there's a whole bunch of zeros, and if you multiply by zero, you get zero, right? So the x component, there is no x component to omega cross r. There is no z component to omega cross r, but there is a y component. The first bit is 0, but the second bit is going to be r omega cosine of lambda. So what does this mean? That means that you can look at it as the right-hand rule. That's a very good way of looking at it, the right-hand rule. The omega cross r is pointing up and down, and omega is pointing a different direction. But it's only pointing in the x or z component. So we can take our hand and say, point your fingers in the direction of the rotation axis vector, omega. You're on your right hand, it's called the right-hand rule. Point your fingers, make your thumb go directly 90 degrees, so you kind of have a flat hand, and your thumb is pointed away from your fingers at 90 degrees. Take your fingers and point them towards the direction of the rotation axis, and the cross product means curl your hand towards the r vector, and your thumb then points in the direction of the cross product, and that is the y component. So r is only z, and omega is both x and y. So you can say curl it towards that, and all of a sudden it's going in that across the surface of the Earth parameter, which would be a west-east. Now then, that's not the end of the story, because I said, remember, it has to go away from the rotation vector, right? It has to go away from the x-axis. So now we cross it again. We cross the result above with omega again, and we plug and chug those numbers for zeros and what have you, and the zeros appear in little dots as we have it, and we end up with no y component, but we do end up with an x component and a z component with those various magnitudes. Notice we have, again, the omega squared r and omega squared r cos theta, which is kind of what we expected from before, because that is the omega squared r cos theta. Well, r cos theta is our original, is the row that we saw before, which is the perpendicular distance from the rotation axis. So the omega squared is because there's two omegas, right? We're not getting rid of their magnitudes, but we're modifying it by the distance from the rotation axis. And so there's where the r cos theta is. The sine theta, omega, I'm sorry, not theta, the sine lambda and extra cosine lambda are because we're looking at something that's changing latitude or a difference in latitude, and we want to see the magnitude of this double cross product at different latitudes. So let's take a look and see what that all rolls up to be. All of the above then says the apparent gravitational acceleration is given below. So we've replaced that original thing, g little tick or vector, with the above in this kind of parentheses notation x, y, z. So x is the first entry, 0 is the y entry, and z is the last entry. So let's look at the last entry first. That makes the most sense because g is downward, so it's negative, because z hat is up. So g downward would be the magnitude of the gravitational acceleration towards the center of the Earth. That's why it's negative. And then there's something that kind of pushes it outward, which has the magnitude of omega squared r cosine squared of the latitude of lambda. So this whole thing, this g tick, and there's this, but the x thing is also there, but there's no g in that because that is x, and x is either north or south. So the north-south thing doesn't have the gravitational acceleration component. Neither does the y component, which is east or west. And there is no y component, east or west, to the centrifugal force, or centrifugal acceleration. Yeah, you hear me make that mistake all the time because it's a fictitious force, but it's a real acceleration. It's kind of a funny thing. Anyway, but it's hard to keep it straight sometimes when you're talking fast. Off we go. So the magnitude of g tick vector is approximately just the z value, because the first bit in x is actually quite small. It's a very small thing because always cosine lambda times sine theta is always going to be something less than 1 times something less than 1, and at either the equator or the poles that's going to be 0. So that's always going to be a very much smaller value than anything else when you take the magnitude. So how do we get the magnitude of this? Really strictly speaking, we take the x component squared plus the y component squared plus the z component squared, and then we take the square root of that. But that's really approximately just the magnitude of the z component, because the x component is so very tiny compared to the other. So when we look at that, the magnitude of it is roughly the gravitational acceleration, with a little bit less due to the centrifugal acceleration away from the center of the Earth. And so that's actually a very small amount. It's about 0.3%. It's a very small amount. It's 300 times smaller than the expected, and that's the maximum it gets at the equator. It's 300 times smaller than the acceleration due to gravity. But that is still measurable, and that therefore means that the Earth bulges slightly at the equator. That is really a real effect of this thing, because the Earth rotates, so it bulges, and that's as a result of the lessening of the gravitational acceleration due to the fact that the entire Earth is rotating. If the Earth did not rotate, there would be no bulge. There it is. Very simple. So it also means that you weigh just a little bit less at the equator than you do at the poles. 1/3% less. So what would that mean? So if you weigh 200 pounds at the equator, if you weighed 200 pounds at the North Pole, at the equator you would weigh 1/3 of a pound less? Yeah, 1/3 of a pound. No, 2/3 of a pound less. That's actually pretty significant. You'd lose 2/3 of a pound by going from the North Pole to the South Pole. That doesn't mean you're losing mass. That means you're losing weight. Weight and mass are not the same thing. So another consequence of it is that the apparent gravitational has a horizontal component going north or south. So that means that a plumb line held still over the Earth's surface deviates slightly towards the equator, That's really interesting. So it swings out towards the equator. At the North Pole, it doesn't swing at all. At the equator, it does not swing at all. At the poles, it does not swing at all. But roughly about 45 degrees is where it has its maximum. And therefore, you can see what the angle of deviation roughly is across the north as you traverse from lower latitudes to higher latitudes. And the theta of deviation, theta is just an angle of deviation, and that's approximately the equation that you see below, which is about the 1/10 of a degree times the sine of twice the latitude. And the twice the latitude comes from the cosine sine theta thing, which is a trigonometric identity, that the cosine of an angle times the sine of an angle, and then the sine of the other angle times the cosine of that angle. The sum of those two things is equal to the sine of angle plus angle. So if they're all the same angle, then sine of 2 omega equals cosine that lambda plus sine lambda divided by 2. That's where the divided by 2 part comes from. It's a trigonometric identities. So essentially, there's a very tiny angular shift or swing that something has due to the Earth's gravitational rotation. Now notice that r is a function of the radius of the Earth, and g is the gravitational acceleration due to the Earth. If you make r, in this case, really small, then the same gravitational force, as you shrink that down, that number will also shrink as well. But if you increase the gravitational acceleration, if you greatly increase the gravitational acceleration, then you're also going to, if you increase it, you're going to decrease the swing. But if you spin it faster and faster and faster, like the omega squared, the faster you spin it, the greater the deflection shall be. So there are some astronomical objects like neutron stars which are spinning at hundreds of times a second, and they have the mass of something like the sun. But their rotation is probably not bulged too much because the gravitational acceleration at the surface of a neutron star is extraordinarily large. There probably is some budging, but that causes incredible stresses across a neutron star. But that's not our point here. We're just looking at the rotation, the swing, the deviation of a plumb line from true as a function of latitude. Well, this always means that if you are leaning slightly southward when you visit New York City. And New York City is roughly about the latitude where it's pretty big. So you are leaning southward no matter what you do. You got a 0.1 degree lean south. That's kind of a funny thing to think about. And if you visit Perth, Australia, you got a 0.1 degree roughly lean north towards the equator. This lean is always towards the equator. So there's a bit more about the centrifugal acceleration and what we experience inside a rotating reference frame. We will always have some sort of effects on the surface of the Earth due to the fact that the Earth's rotation is there. We can measure the plumb lines, that there is a deviation of this from true due to a hanging object, because weight is different than something that hangs, and so if you have a long enough measurement, you can actually probably see it, but that is a very, very tiny measurement, and hard to, not difficult to measure, but you can imagine some methods by which we can measure that. As well as you have some lessening of the weight and the bulging of the Earth, and the bulging of the Earth is a measurable quantity. And that's important to note. It's also important to note that the bulging of the Earth is due to the rotation of the Earth, and that's actually something that can be measured. So we're finding ways to show that both the Earth is a sphere and is rotating. Next time we're going to go and look at the not the centrifugal or centripetal aspect. We're going to look at the Coriolis effect, which is the second term in that big long equation at the top, and eventually that'll get us to a Foucault pendulum, which is the measurement of the Earth's rotation. All right, we'll see you next time.